Frontier meaning is something at the front or at the border. You might have seen the names Frontier Gandhi, at the border. So in the borders you have the front, they call it as the frontier. Molecular orbital theory is mixing of orbitals and the resultant orbitals are there. The frontier molecular orbital theory is something which is at the forefront. It is like you are taking the molecular orbitals at the valence level. They are the orbitals that have the electrons that actually go into reactivity. So these form the descriptors, molecular descriptors. In the last class you have seen the descriptor log P, distribution coefficient. So today I am going to share the screen. Here it is. And I'm going to discuss this with you about the frontier FMO theory. The reason is we have so many things. The best three things which I'm going to tell you is one is the reactivity in chemistry. Reactivity in chemistry. That is the first thing. Here you take only the valence electrons. Second thing is fire or plasma. Have you ever wondered what if fire is, what if plasma is? You might be able to classify solid, liquid, gas, and three other phases: solid, liquid, gas, plasma, bosons, and fermions. But you might not have classified this fire or plasma based on the FMO theory. So this is very interesting. The third thing that I am going to correlate with this descriptor is the spectra, or by that means the color of the complex, or the spectrum, the original spectrum that is there, and the result that is there, that is the outcome is the fluorescence. Okay, so these three things can be really be explained by FMO. Frontier means at the front. Okay, so here is the brief description about this frontier molecular orbital theory. It was developed, look at how old it is, 1960. Now we aren't even into it, and we haven't seen much about the FMO theory. The Japanese scientist Kenichi Fukui, he has got so much to his name. Fukui function is there. Fukui function is able to classify molecules into nucleophilicity and electrophilicity. It's a very, very extensive work and very interesting work. The Fukui recognized chemical reactivity can often be explained in terms of interacting HOMOs and LUMOs, that is the highest occupied and the lowest unoccupied molecular orbital, plus singly occupied orbital. So this is a qualitative approach. Look at this qualitative approach. Qualitative means it is of some quality. So if you change something, it may change. It depends on the outcome, depends on the quality. Quantitative means outcome depends on the quantity. So if you mix HOMO plus LUMO, you get a bonding orbital. If you mix HOMO plus HOMO, we have anti-bonding orbital. That is to say that mixing of the same symmetry orbitals, same, exactly the same, that doesn't have any effect. Okay, so that in a sense we call it as an anti-bonding orbital. And in the same way, LUMO plus LUMO is null interaction, unoccupied. There are no atoms there, unoccupied orbitals are there. And this is a newly introduced term that we call as the singly occupied molecular orbital. This usually, we consider it under free radical additions. Free radical additions. Later, it was developed by Woodward and Hoffman. I think you have this Woodward-Hoffman rule in organic spectroscopy. So I was telling that the third point here is the spectra is all about is the Woodward-Hoffman rules. Okay. Woodward Hoffmann rules in the late 1960s used to explain apparently the diverse set of reactions involving pi systems. With pi systems, I think you know cycloaddition reactions, pericyclic reactions in photochemistry is there, including famous Diels-Sauter cycloaddition reaction, often used the approach to explore transition metal complex. And here, Fukui and Hoffman were awarded 1981 Nobel Prize lectures. So there are a lot of key lectures, right? I will just invite one image of the what FMO should actually look like. Here it is. Right? This is the I need you to give importance to this HOMO and LUMO. Here you have HOMO and here you have LUMO. Now you can see that the shaded portion is there, unshaded portion is there. This is unshaded and this is shaded portion. You can consider this shaded portion as something of the same charge or in the same phase. I think you know phase, just like you have solid phase, liquid phase. You have the same wave phase and wave function. For everything under state, everything that is plane we consider as the same phase. So you can see that the same phase is lying at the bottom in these two bonds. Same phase is lying in the top in these two. Here you have opposite. And in the top you have unshaded portion. In the bottom, in the top you have unshaded portion. In the bottom you have unshaded portion. This is not very difficult. This has become very easier. Why? The softwares, particularly Chemcraft and the other software I told you the other day, ChemSketch, they are able to identify it in terms of the green color. This may be in top and this may be at the bottom. So this particular top portion may be green in color and this particular bottom portion will be red in color. Okay, so red and green we consider as different phases. Okay, they are represented by Chi, 1, etc. So here this is a kind of reaction which gives you the idea of overlapping. That is, here you can see that there is an arrow mark. And arrow mark means you know that this is overlapping. It rotates like this and this comes like this. That is, if you have two pi orbitals, p orbitals or pi orbitals. Pi orbitals means they are the same. There is possibility that these two things can overlap, and there is possibility that these two loves will overlap. Overlap இப்படியே நடக்கலாம், இப்படியே நடக்கலாம். So here for this to overlap with this has to bend down and this has to rotate. Okay, so you find this in cycloaddition reaction. You have a separate department there, cycloaddition reaction called as okay, that means you know in the descriptor part, the HOMO LUMOs, you know, they actually take up the very good reactivity part. And here you can see in the cycloaddition reaction. I'm not going into much details, but I'll just highlight this. This is the first slide. This should be the first slide. So our computational chemistry will be able to give you Chi 1 and Chi 2 What is psi 1? In psi 1 you have both these shaded. These two are unshaded. That is in psi 2 you have bottom shaded, here top shaded. That you call it as the lowest unoccupied molecular orbital and highest unoccupied molecular orbital. And here again the same thing is there. In terms of the alkene, that is the there is sort of reaction. An example you mentioned, 2 electrons is a single pi bond FMO3. Here identifies the HOMO and LUMO component of the system. That you can see it here. The diene, which has 4 electrons, diene, dienophile, is conjugated pi system and can have HOMO and LUMO identified within FMO3. All 4 options are there. This. All the 4 are shaded bottom. Here 2 at the bottom, 2 at the top, bottom, top. Here 1 at the bottom, next one at the top, next one at the top, next one at the bottom. D. Now here this is an alternate thing. So orbital overlap ultimately defines reactivity. கெமிஸ்ட்ரியில நாங்க பாக்குறது என்ன, எவ்வளவு எதுல ரியாக்ட் ஆகுது, என்ன மெக்கானிசம், அதுதான் ஃபைனலா பாக்கணும். எந்த ஒரு சப்ஜெக்டும் எடுத்துக்கங்க, you take any subject, you're finally going to see the reactivity. And if you want to know the reactivity, it is only the frontier orbitals. It is never the nuclear or core orbitals. Nucleus picture la varadu idhula. Nuclear chemistry na adu thaniya chemistry, thaniya field. Nuclear chemistry doesn't come into the picture. Only the core pictures, core levels are there. I mean the orbit valence levels are there. So that is an example here. And here you can see the 2 electrons, the same spin. This is a violation of Pauli's exclusion principle, that says that no 2 electrons can have the same set of 4 quantum numbers. That means you cannot have the same electron with same symmetry in the same orbital. That is to say, that refers to a particular atomic orbital. But when it comes to molecular orbital, you can have an orbital where you can have two electrons occupying the same symmetry. Right? So Pauli's exclusion principle is purely atomic in nature. It's not molecular in nature. Whereas FMO theory can explain you how you can have 2 electrons of the same spin in the same, nearly the same orbitals. And here you have inverted electrons. You are calling it as a singlet diradical. You call it as a triplet diradical. So the spin is half plus half. So 2 into 1 plus 1. The formula is 2s plus 1. So 2 into s plus 1 will give you what you call it as a 3, which is what you call it as a triplet. And the triplet da inge potrukka. Triplet. Okay. Here you are not able to see anything in singlet or triplet. The structure remains the same. In the structure same there. But when you look into the spin, this is a separate spin and this is a separate spin. Right? So what is the important point here is, by changing the electron arrangement inside the orbital, you can bring about the reactivity change. The first step that you do in any chemical reaction or preparation is heat it, reduce the pressure, or do a mechanical thing. When you do such thing, these things happen. If you examine the phase that terminus of the diene and dienophile, you find that HOMO-LUMO interactions are phase matched. Phase matched அப்படினா இது இதோட react ஆகும், இதுக்கும் react ஆகாது. Okay, the same orbitals with same symmetry will overlap, with different symmetry will not overlap. Here also you can see the same thing. In the FMO diagrams above, the sizes or coefficients are the same. The coefficient அப்படின்னு வந்தாலே வந்து coefficient means it is a calculated from Schrodinger equation. You don't call pi bond or sigma bond. You call an electron with pi symmetry, you call an electron with sigma symmetry, you call an electron with non-bonding symmetry. That is the actual modern science, modern chemistry, advanced chemistry. Okay, usually there are differences. The rule is that the coefficient match as well. Small with small, large with large, positive with positive, negative with negative, blue with blue, red with red, like that they are matching. Visualizing thing you can achieve using the several softwares that are there. Thus, regioselectivity of the cycloaddition can be explained. Okay, so now coming back to our description part, the molecular orbital things are very easy. So you have two atomic orbitals and you have two molecular orbitals. These are AO and this is another AO. This is MO and this is another MO. And you have two electrons here, two electrons here and two electrons here. Here also you have two electrons. Okay, this is joined by means of this is, you have to scale it, energy. Okay, delta E, change in energy. And these two atomic levels are at the same energy level. Let me just take 5 kilocalories. And this will be 10 kilocalories higher in energy. And this will be 2 kilocalories lower energy. That is to say, an MO of lower energy is there. Another MO of higher energy is there. Okay, if I draw it like this, an electron from here goes to this. Okay, so this is unoccupied. In some computational chemistry classes, they are called as the Rydberg law. Rydberg valence core. So remember the third point I just told at the beginning, fire. What is that? Plasma is there. Plasma is, an electron jumps from here to this particular place. When it jumps, it changes its spin. Earlier it was singlet, it becomes triplet. Triplet states have, sometimes they have got longer relaxation life. This again has to come back. Okay, what is the beauty is that everything that gets excited from HOMO to LUMO or singly occupied to unoccupied molecular orbital has to come back. When it comes back, it emits some radiation. Okay, this particular emission of radiation is what you record in spectra. And there are some electrons that stay like this. This for one particular molecule. In a bunch of molecules, in a particular gram, you will have up to 10 million such molecules. You will have such kind of levels. Okay, that you will call it as the plasma. Okay, plasma means you have a level from here, another, it goes excited, this is what you call as the ground state and excited state. Remember, you can call ground state as HOMO and you can call excited state as LUMO. This is the place where electron rearrangement takes place. Rearrangement or relaxation or spin change. R equal to NH2 will have a different HOMO. R equal to NO2 will have a different HOMO. R equal to OCS3 will have a different HOMO and LUMO. R equal to OCOR dash, it will have elongated pi system. Okay, so you can increase the pi system, you can increase the number of highest occupied molecular orbitals and lowest unoccupied orbitals and bring it into the reactivity. Okay, what is the final conclusion that I am going to make is, you have to remember many theory have failed. Sigwig's theory, valence bond theory, all these things are only for a particular level. Frontier molecular orbital theory is the most successful theory because it can be explained based on quantum chemistry. Quantum chemistry, which gives you the psi 1, psi 2, psi 3, psi 4 orbitals. I have shown these orbitals in the chemcraft, and you have also seen how the electronic arrangement is there. Okay, so that you can simply change, and it varies from molecule to molecule. Molecule to molecule, it varies. Therefore, it's a very good property of molecule. Hence, it is a good descriptor. Okay. Now, what we have seen is, what we have to finally conclude is that when biological activity of a molecule, is dependent on its dipole moment plus polarizability plus ionization potential minus LUMO plus HOMO. Okay, and this is a general qualitative QSAR equation. So I have told you what a QSAR, quantitative structure. This is a quantitative structure activity relationship. So you can have it, I can call it as D, I can call it as P, I can call it as I will call it as L and H. So therefore, biological activity is equal to D plus P plus I minus L plus H. Okay, this every D, P, I and L and H, everything you can calculate it. Sometimes what happens is, biological activity will be equal to 2D plus 4P plus 0.5 I minus 6L plus 2H. It can be calculated. So remember, this is a statistical approach. Okay, so you keep on changing the equations. There are several softwares. For example, one software which is very famous is called as the Build QSAR. Is a software. There you can have a few molecules, 40 molecules you can have, derivatives. After having 40 molecular derivatives, you can calculate the descriptors, calculate molecular descriptors, including what should I say, including surface area, surface volume, nucleophilicity, basicity, acidity, and polar surface area, van der Waals surface. So many properties keep changing. Okay, and when you see so many properties keep changing means you have to, the scientist now who does the research, he stitches the molecule, changes the molecule in several ways so that he arrives at a particular conclusion, and that is called as the quantitative structure activity relationship. It is nothing but QSAR. There is a separate study also called as the quantitative structure toxicity relationship. This is QSTR. In every molecule drug that you prepare, that you discover, that you want to show, you have to measure toxicity. Unless you describe the toxicity, it will not be accepted by any pharmaceutical industry or industry. How much effective your drug is, how much toxic your drug is, what is the side effect in mice, what is the side effect in rabbits, or what is the side effect in any animals, and then you bring them, after measuring the toxicity, you bring them into human beings, and that is what you call as the clinical trials on human beings, and finally you find out how successful a particular drug is. Okay, in the previous class we have seen log P as one of the very good descriptor. Log P, distribution coefficient, log D. So this is, I told you that partition coefficient in octanol by water. So this is aqueous layer, this is organic layer. ஒரு ட்ரக் போட்டிங்கன்னா aqueous layerல எவ்வளவு நேரம் இருக்கும், உடனே ஆர்கானிக் லேயருக்கு எப்படி போகும், blood ஆர்கானிக் லேயர், வாட்டர்ல இருந்து ஆர்கானிக் போகணும், அது ஒரு good property. Log P is measured by several softwares as shown. ACD chemistry is also there, and there is another software called as the mole inspiration, which measures the log P value. Log P value can be calculated very well. Okay, so we have come to a conclusion that frontier molecular orbital theory, HOMO, LUMO are essential for describing the reactivity, for describing the spectral properties, for describing the phase. These three things are very essential. And if you do not know any practical way to measure this, you can always refer to the theoretical calculations where you can calculate these particular descriptors and arrive at a conclusion that these properties are very good. Okay, so molecular descriptors are very essential in establishing the biological activity. Biological activity includes bacterial activity, fungal activity, anti-cancer property. So many properties are there. There are so many papers in the present day, particularly related to this particular COVID-19 virus. Each day there are at least 200 to 300 papers. People do a lot of research, people do a lot of work. They include QSAR. There is one field also called as 3D-dimensional QSAR, which relates properties in third dimension. Okay, so we will go through this. In my YouTube lecture, I'll publish the notes also. You just have to write when they ask you the molecular descriptor about HOMO and LUMO. Thank you for joining me. If you have